Rationalizing expressions. So we start with just looking at fractions with radicals. So if I had a big square root and then a fraction inside, square root of a over b, we can write this as the square root of a over the square root of b. Separate it into different square roots, simplify them as needed, and go from there. If we had something with common factors, we can also divide and simplify that. So if I had something like the square root of 8 over the square root of 2, we can look at it as being the square root of 8 over 2, which really makes it the square root of 4 over 1, which back in the separate idea would come out to just be 2. Square root of 4 being 2, square root of 1 being 1, 2 over 1. So if you have a fraction with just the square roots in them, you can reduce them just like you would any other fraction. You don't have to change it back to a full radical. Inside, to simplify, we can just look at it and say, yep, that becomes 4 over 1. It's going to simplify to be 2. So that's something nice with fractions. The exception to that, which we're not covering right here, is that 17 through 20, when you'd had multiple terms. If it's strictly fraction, a number over a number, you can reduce those. Different scenario, we're not there yet. So I can give you a variety of those. It's really simplifying like we've already done. Multiplication, division have that relationship, or multiply, we put them together. Division, we reduce, and it's the same idea. So we'll still see the common trend. The new part we have is if we get a radical in the denominator by itself. 1 over, let's say, the square root of a. Now, although that seems nice, we can't reduce it, and it's a nice way to write it, unfortunately we cannot leave an answer like that. We cannot leave an irrational number, a square root, in the denominator. If you have that, we have to what's called rationalize the denominator. Okay, we called it an irrational number. We need to make it rational, so we rationalize it, it being the denominator. To do that, we're going to multiply the top and the bottom by the same thing. So really, when we multiply the top and the bottom by the same thing, we're multiplying the whole thing by 1. But what we're going to multiply it by is that denominator. So if it is 1 over the square root of a, I'm going to multiply by the square root of a over the square root of a. In terms of the math behind it, we're really multiplying by 1. What we do is we're changing it. It's kind of like when you reduce a fraction. It's still the same value. You just kind of change its appearance a little bit. What this is going to do is it's going to clear out the square root in the denominator. It's going to bring it up and leave it as a term we can accept. Now, the reason we do that is because if I multiply a rational number by itself, it's like saying that I have the square root of a squared. And what we've kind of started to see is we have 2 of them, so they would come out to the square root, or really that when you have a square and a square root, they kind of wipe each other clean. We're not going to say cancel each other out. Cancel is not a good math word, but they kind of do. And really it leaves us with that value on the bottom, and then the radical is moved up. It still represents the same value. If we started out, for example, with 1 over the square root of 2, which is a common one, and we multiplied the top and the bottom by the square root of 2, the top, of course, becomes the square root of 2, and what's the bottom become? 2. And the square root of 2 squared, 2 of them just leaves the number. So square root gives you the number. Now, I plug 1 over root 2 in a calculator, and I plug in root 2 over 2 in a calculator. It gives me the same answer. We just accept this term is the proper way to write it. Same way you always have to reduce a fraction. This one we call rationalizing the denominator, moving the radical up. So let's go and look at 1 over root 7. Again, we multiply the top and the bottom by root 7. What do we get? Yeah. So whenever it's just 1 over a value, it becomes the radical moves up, and the bottom number is it without the radical. Yeah?
Say if the top number is square root of 4, you have to simplify that to 2?
You would, yeah. Yeah, we'll add some more in here. So let's bring more radicals in. So really, when we look at this today, we have fractions there. We're going to simplify them, like we have up here. Or we're going to rationalize the denominator if there's no radical to simplify it with. So anything from here on out is just kind of using those two rules, picking different values, and playing with the rules that we have here. So let's go square root of 42 over the square root of 14. So we still may have to look at our simplifying, simplest radical form to help us get somewhere. But looking at square root of 42 over the square root of 14, what do we see? Can I reduce 42 and 14? Yeah. What are they both divisible by?
7.
Okay, so that gives me square root of 6 over what?
7.
Can I keep going? So then it becomes square root of 3 over square root of 1, which is just square root of 3. No radical in the denominator, we're done. Not the only way to approach the problem. You could have looked at them and maybe tried to simplify, get in the simplest radical form. Does that work? Can 42 be written in a different form? Does it have any perfect squares in it? Six and 7, that's 2, 3, and 7. It wouldn't, so we probably actually wouldn't want to do that. How about square root of 48 over the square root of 12? Kind of. It'd be square root of 4 over square root of 1, which just becomes 2. Yeah. Don't forget it's still in a radical whenever you simplify it. So you're left with square root of 4, you just make it into 2. How about square root of 8 over 98? Separately, we think of 8, we know we can get it to a simplified radical form. 98, we've actually, that was a number on one of the homework problems we went over, but we could maybe work through that, find a perfect square. Simplify them, see if we get them to simplified radical form, and what we have that. Or, what's our other option? Can we reduce those fractions? If you have a fraction, reduce it. Always reduce. I don't care what process you're doing in the problem. Well, I guess unless you're adding fractions, we don't want to reduce it because we want to have like denominators. Other than that, anytime you get a fraction, you reduce it, you get smaller numbers, it makes things easier. So we go to that first. What can we divide both of those by? Divide them both by 2. It gives us 4 over what? 49. Is that a good sign? It is. 4 was nice. It pops up. Oh, it's a perfect square. So is 49. What's our answer? Square root of both. We get 2 over 7. And I hit the plug again. It'd be really nice if my computer would log on. All right, now we bring in the third root, or the cube root. Okay? When we've rationalized the denominator so far, let me step back. I'll write the example to just square root of 5. Okay? Now, we did square root of 5, 1 over the square root of 5. We multiplied the top and the bottom by the square root of 5 to get us root 5 over 5. Now, why that worked in getting rid of the radical in the denominator, because if we didn't have 2 of them, the pair of 2 came out of the square root, it simplified. Now if we look at the cube root, or the third root, I still need to get rid of the radical. How many 5s do I need to multiply in the denominator? How many do I already have? How many more do I need? 2 more. So I'm going to do 2 more. Really, you've got to finish out the set. Finish out the set on the denominator, and then whatever that requires, you put that to the top. So I also am going to do 2 up there. Now, I like to leave them separate and just think 5 and 5. Really, that's the cube root of 25. But if we start doing that, then we got different numbers and we could be adding extra stuff and missing things. But in either case, what's my denominator now going to be? I got 3 5s. They're out. 5 left over. Numerator, we put together. It's the cube root of 25. Okay? Doesn't simplify because one's a radical, one's a number. You can't make that root 5 over 5. You just leave it as it is. Okay, but so far we've been looking at, and we always kind of have that 1 up there. Let's make this 7 over the cube root of 4. Now, do I want to finish out the set of 4s on the bottom? What's easier to do, though? Not 4. 2s, right? How many 2s do I have down there? I got 2 already. So I could say, all right, 7 over the cube root of 2 times 2, and all I'm going to have to add on is another 2 to the top and the bottom. Gives me 3, takes care of it, it's gone, it's just a set. And the top is 7 cube root of 2 over 2. It's reduced, don't do anything else, it's done. The other option, well, let's see if it gives us the same answer. If it doesn't, well, then we're probably in trouble. What if we went with the 4s? So now if we did cube root of 4. How many more 4s do we need? Okay. So I got 7 cube root of 16 over 4. Is it different? They're the same answer. Why do they not look the same? What's not simplified? The cube root of 16. And this is why I mentioned you always got to just check. Make sure when you get to that end that you can't simplify it any further. Off to the side here, let's look at the cube root of 16. Well, that's 4 and 4, which turns out to be 4 2s. So the cube root of 16 is actually what? Simplified. 2 cube root 2, right? So, let's go back, and now we have 7 times 2 cube root 2 over 4. We reduce 14, cube root 2 over 4, and it comes out to be 7 cube root 2 over 2. So it had a little bit extra step. Now, the reason was we picked a larger term to find the to get rid of in the radical, and that just added the fact we had to reduce later on. If we would have kept with the 2's, we would have done that. And even if you go out and every single time you try to find the smallest, you may pick the larger one at a random time. As long as you go back and try to simplify, you'll be fine. Okay, it's not that it was wrong, and we just had to keep simplifying it down. It's almost like reducing a fraction. You've got to get to that final answer. All right, let's go the fourth root of 5 over 8. I want you to try this one. See what we get to. Walk me through it. What am I going to do first?
Simplified the 8, so it was 3 2's.
Okay. Now what? What am I multiplying by? Top and bottom. Fourth root? Yeah. Fourth root of 2. Okay. Don't use 8. 8's going to be too big. Keep it smaller. So that makes the denominator into a nice 2. What's the numerator going to be? Yep. Fourth root of 10. Perfectly fine. It's reduced. Do not write it as 5 over 1. 1 is a radical, 1 is a whole number. Do not reduce them. Okay, it's like separate variables trying to reduce those. Leave it as that, it simplifies down. Okay, that's about as scary as I can make it. You get large roots, you have some of them, you got to find the rest, the top stays a radical, and you have to multiply it. Now, if it was like the previous one up here, where it just had a number, well, you just treat it as the number, it stays in the form. So, you can reduce them when they're fractions, like we said here. Radical in the denominator, you have to move up. It's called rationalizing the denominator. Do not leave the answer down there. And really, again, this is more the simplifying. Getting into that simplified radical form.